Lewis structures, the non-octet breaking ones. Our goals for this video will be to learn how to draw Lewis structures a little more in depth than what we have been doing them for molecules that still do not break the octet rule. So we'll be trying to get it so that each atom has 8 electrons. We're then going to also learn how to assign formal charges for the atoms within a molecule, since this is going to be needed for lots of different situations. Here are some general guidelines for going through the process of making Lewis structures. Be sure to do the first and last step, even though once you get comfortable with them, these become very easy to forget to do. But they're imperative for making sure that you do everything correctly. Each time that we go through to make a Lewis structure, we're going to start by counting up all the valence electrons from each atom. Remember to only count the valence electrons, not the total electrons. We're going to total these up and then write the number somewhere so you can be sure to check this as you're going throughout the rest of the process. From here, we need to connect all the atoms. Just use a single bond to connect everything. This makes what we call a skeletal structure. Each bond represents 2 electrons. Find out how many electrons you have remaining and distribute them to each atom so that you have 8. If you cannot do this because you do not have enough electrons, then that means that more bonds need to be made. Or, in other words, more electrons need to be shared. Make double and triple bonds as are needed. Now, this part we're going to talk about more in the next podcast, but I wanted to put it into the stepwise just so that you recognize that this is something that by the time we're done with this topic, you'll need to know how to do. All right. Then what we need to do, there's often multiple ways to go about making these double bonds or triple bonds, and so we're going to need to know which way to do it. So what we'll do is we'll check formal charges, and we're going to try to minimize them. This is all going to make a lot more sense once we do some examples. Please remember that there isn't a hard and fast process for making Lewis structures. There's a little bit of playing around with them. So for a while, you're going to be doing a lot of guess and check. The more that you do, the more patterns that you're going to see, and the easier that it's going to be to get things right quickly. And then also at the end of this podcast, after we've gone through the examples, I'm going to give you a few tips and tricks for doing these a little bit more quickly. They're things that if you did enough of them on your own, you would catch the patterns with, but we'll hand them out to you here as well. And then our final step, after we're all done, is double checking, making sure that you have the correct amount of electrons present. Before we get too far into our discussion of Lewis structures, we need to discuss a concept called formal charge. This is the charge that the atom would have if all of the electrons in the bonds are shared equally. It is determined by taking the electrons that the atom owns in the molecule and subtracting that from the number of its original valence electrons. So the original valence electrons we find from the periodic table. Now, what about how many it owns in the molecule? Its lone pairs are counted completely as its own. So each atom that has a set of lone pairs, it owns those lone pairs. So let's say an atom has 3 lone pairs. That means that it has 6 electrons. It gets 1 electron from each bond then. So let's say that the same atom that had the 3 lone pairs also has 1 bond. So it would have 3 lone pairs, or 6 electrons, plus 1. So 6 plus 1 equals 7. So it owns 7 electrons in that molecule. So then its formal charge will be whatever you have from the periodic table minus 7. This also is going to make more sense as we do some examples. Now let's look at some examples. So here we have nitrogen. We look on the periodic table and we find nitrogen, and we see that for each nitrogen we have 5 electrons and we have 2 of them, which means that we have 10 electrons total. So we'll write that up here so we keep that in mind as we're going throughout. So from here, we need to connect our atoms. Now, in this case, we just have 2, so that's pretty simple. Now, let's try to distribute everything so that we have a full octet. So if we try to do this, we have 2 electrons in the bond. So 2, 3, 4, 5, 6, 7, 8, 9, 10. Well, shoot, we're out of electrons. So since we don't have enough electrons, we'll say, well, that can't be right. So I'm going to need to make more bonds. Now, of course, when you're doing this at home, my suggestion would be pencil so you don't have to keep crossing them out. So we need to have 4 more electrons. So what we could do is we could just draw this, put a double bond, and try to distribute the electrons. Now what you're going to see is you're still short. You're short by 2 now. And so we need to draw 1 more. So it may be good practice there to stop and go ahead and see that with the 2 bonds, you don't have enough electrons. So now let's try this. We have 2, 4, 6, and then 2 here is 8, 9, 10. So 2, 4, 6, 8, 10. We're all set. And then for each nitrogen, 2, 4, 6, 8, 2, 4, 6, 8. Now here we have a more complex example, but we will start it out the same way. So we look at our periodic table, and we see that boron has 3 electrons, and that nitrogen has 5 electrons, and each hydrogen is going to have 1, but we have 6 of them. So we have 3 plus 5 plus 6. Okay, from here we have to build our skeletal structure, so we have to figure out how these things are connected. Now, something special about hydrogen, and this hasn't changed from when you were in high school. Hydrogen doesn't have an octet, right? Hydrogen is only allowed to have 2 electrons because it only has that first S shell. So we know that hydrogen can never be a central atom. We know that hydrogen can't be bonded to multiple things. And so what we'll do here is we'll see that we actually kind of have a hint in how it's set up. The problem gives you major hints here, and you should always be looking for that when you do these examples. We have BH3, like this, and then the boron and the nitrogen must be connected because hydrogen can't be connected to anything else. And so we're left with that. So that's our skeletal structure. Now let's figure out how many electrons we've used up and what we have left over. So we can see we have 2, 4, 6, 8, 10, 12, 14 electrons used, and we have 14 electrons here, so all of our electrons are used up. So now let's make sure we have an octet. 2, 4, 6, 8, so boron has an octet. 2, 4, 6, 8, so nitrogen has an octet. And we are all done with this one. Now let's look at an ion. So this is a little bit different, and it's a little bit shoehorned in order to make sure that we get a few different concepts covered all at once. So we're going to start the same way as before and say that we have 8 electrons. Now notice xenon's a noble gas, so we're not used to seeing that in compounds a lot, but it's okay. Xenon can be in compounds. And we have fluorine, and we have 4 of those. So if we were to just leave it at that, we would have 36 electrons. But we need to account for something here. And this has a +4 charge, which means that it doesn't actually have the 36 electrons. It has 4 less than that. So we need to subtract 4 to give us 32 electrons to work with. Now, from here we can go and continue on. So fluorine, since it's a halogen, it prefers to just have 1 bond and just have 1 electron, or 1 extra electron to give it an octet. And so fluorine will be our ligands here. It'll be our outside. And xenon will be our inside. Now, there's not a lot to be done with fluorine or any halogen on the outside like this. So let's just give it its octets, because we can assume that we're safe there. And xenon already has an octet. And we can count everything up. So on each fluorine we have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. So we're all done and we have our fully octet system. We have all of our electrons. Everything is set. Now let's go over a couple of tips and tricks. These are one of those things that I guess you could memorize if you want. If you do enough of them, you'll already have them memorized. So it may be better to just keep this handy with you, keep some notes on this handy with you when you're doing these, and eventually it'll just become second nature to you. So boron is often going to have 3 or 4 bonds and 0 lone pairs. And you may be thinking, okay, well that means it doesn't have an octet. We'll talk about that more next video. Carbon most of the time have 4 bonds, which means that it has an octet already, and then no lone pairs. So usually if you can get it set up so that carbon has 4 bonds, just start with that in some way. Nitrogen often has 3 bonds and 1 lone pair. Now, we've already seen an example of nitrogen where it actually has 4 bonds, and that's fine. But most of the time, it'll have 3 bonds and 1 lone pair. Oxygen, typically 2 bonds, 2 lone pairs. Again, these are not hard and fast rules. You can change these around when needed and when convenient. It's just the most common way of doing it. Now, the halogens are usually going to have 1 bond and 3 lone pair. A giant exception to this becomes when your halogens are your central atom, and that never happens with fluorine, but you'll see it with chlorine and iodine sometimes. Now, sulfur and phosphorus can be similar to either oxygen or nitrogen respectively because they're right below it on the periodic table. But what we're also going to see in the next video is that these often break the octet rule and instead will have 6 and 5 bonds. So you'll often see sulfur and phosphorus with 6 and 5 bonds respectively. All right, now that we have gone through and we have drawn Lewis structures for all of these, we should go back and do formal charge. Now, because I've been trying to keep this relatively simple, the issue of having to assign formal charge didn't come up. And I did that on purpose because those are much more complicated examples. However, as far as good practice goes and learning, we should learn how to do this. So let's move back to here and start assigning formal charges for each one of our atoms. All right, so N2. So for the nitrogen, let's look on the periodic table, see how many valence electrons it has. And you can see that it has 5. So we're going to start with 5 electrons. And then we're going to see how many does that nitrogen own in this molecule. So you're talking for formal charges, remember each atom separately. So we have 1, 2, that is its own. And then it gets 1 from each bond. So 1, 2, 3, 4, 5. So we subtract 5. So we get a formal charge of 0. Now, the same thing will happen for the other nitrogen, but let's go ahead and do it just so you remember that we're doing this for each individual atom. So this nitrogen has 5 electrons from the periodic table, and it has 1, 2 of its own, 3, 4, 5. It gets 1 from each bond because that bond splits the 2 electrons evenly between the 2 nitrogens. So again, 5 minus 5 equals 0. All right, moving on. Okay, here we have our little bit more complicated example. So I'm going to skip doing it for the hydrogens because they're just a little bit more boring, and we're going to work through the formal charges for the boron and the nitrogen. So for boron, we're going to go to the periodic table and we're going to see that it has 3 electrons. We're going to subtract out how many it owns from this molecule. So it doesn't have any lone pairs, so all we have to worry about is the bonds, and it gets 1 electron from each bond. 1, 2, 3, 4. So 3 minus 4 is -1. And that's equal to the formal charge. Now let's look at nitrogen. We go to the periodic table and we see that it has 5 electrons. Now if we come over here, we'll see that it has 1, 2, 3, 4 electrons because it has 4 bonds and no lone pairs. So it has a formal charge of +1. Now, the xenon with 4 fluorines attached, and we have an ion. So what we'll do here is Well, let's just do each fluorine. They're going to be the same because they're all laid out the same, so this is true for every fluorine. So we look at the periodic table, we have 7 electrons. And we come over here and we see how many the fluorine owns. So remember, its lone pairs are completely its own. And the bonding electrons, each one gets 1. 1, 2, 3, 4, 5, 6 from the lone pairs, and then 1 from the bond. So we're going to subtract 7. So 7 minus 7 equals 0. So the fluorines have a charge of 0. And you wouldn't normally have to write that, but I'm just going to write it to show you and remind you that that's true of each fluorine. Now let's look at the xenon. So from the periodic table, it's a noble gas, and so we have 8 electrons. Now we go over to the molecule and we see that it doesn't have any lone pairs, and it has 4 bonds, so it has 4 electrons that it owns. And so it has a +4 charge. Now, something that's good to note here, and it was true in the other cases too, but it didn't get brought up quite as explicitly, that the charge of all the formal charges, it has to add up to be the charge on the molecule. So in all the other cases, you can see that it adds up to 0 because there was no charge. Here, you see that if you add them all up, they add up to +4. And that's because that's the charge on the molecule. So that's a good double check you can do to make sure that you're doing it right. All right, so now that we have gone through all of this, you now know how to make Lewis structures. And I've alluded to the fact that not everything follows the octet rule, and we'll do that next video. But now you know how to make ones that do follow the octet rule. And you're going to play around with it and, you know, get a feel for it, because it really is sort of, you know, getting a feel for it, not hard and fast rules, knowing when you need to add extra bonds, etc. And you also know how to assign formal charges, which when we get into more complicated Lewis structures, which we'll do in class and maybe a few in other videos as well, and that's going to become really important. So even though here it didn't make a huge difference, do make sure you know how to do it and you've practiced doing it on the simpler compounds so that when we do it on the bigger ones, it'll make more sense.